Hello viewers, welcome to the session on quantum computing. In this video, I dive into the fascinating world of quantum computing, starting from the introduction to quantum computing, then exploring qubits and their features, then about the representation of qubits, which is crucial for understanding quantum systems. Before we delve into the quantum computing, let me take a moment to recollect Moore's law. According to Moore's law, the number of transistors on a microchip doubles approximately every 2 years, while the cost per transistor decreases. This has driven the exponential growth in computing power, leading to the remarkable technological advancement what we are experiencing today. Observe the graph with the number of transistors on a microchip in different years, which follows an exponential trend, and it illustrates the Moore's law. This has worked for a long time, but now we are approaching the physical limits of miniaturizing transistors. Transistors have become so small, nearly the size of atoms, that further shrinking them poses significant challenges. This miniaturization has brought classical computing architectures to a critical juncture very difficult. This shift forces us to think beyond the classical architectures and explore new paradigms. This is where quantum computing comes into picture. Unlike the classical computers, which rely on binary transistors, quantum computers leverage the principles of quantum mechanics to perform computations. Instead of relying on transistors like regular computers, quantum computers use the principles of quantum physics such as superposition and entanglement to process the information in completely new ways. This makes them to process and solve the problems that are practically impossible for classical computers. So, quantum computing does not extend Moore's law, it represents a paradigm shift. So, quantum computing is not about making computers faster, it is about solving problems that regular computers would take a long time to handle, like cracking advanced codes, optimizing huge systems, or simulating molecules for new medicines. Let us see how the quantum computer looks like. A quantum computer looks very different from that of the laptops or desktops we are used to. The picture shows how the quantum computer appears. You can observe that it has a refrigerator-like structure. The quantum computers operate in extremely cold temperatures, often close to absolute zero, to maintain the delicate quantum states. Their main components are typically housed into a cryostat, which is a cylindrical or box-like cooling system, resembles a refrigerator or a large chandelier. Inside the cryostat, you will see a complex structure with golden shiny wires and plates hanging down, which is often called the quantum chandelier. And this part of the quantum processors, cooling and the wiring system. These wires carry signals to and from the quantum bits. The actual quantum processor where the qubits are located is quite small, typically a chip-like structure at the bottom of the chandelier. These qubits are often made from the superconducting circuits or trapped ions depending on the technology. Hundreds of wires and cables connect the quantum chip to the control and measurement systems. These are needed to send signals to the qubits and read their states. Shielding is used to protect the qubits from noise and interference. The quantum computer is controlled by a separate set of classical computers that send instructions, manage cooling, and process data. This control systems usually occupies raw CAF equipment. The cylindrical cryostat, where the quantum processor and the cooling system is placed, is shown as A and D. The support system for what's inside the cylinder, like power supplies, cooling gas, control boxes, referred and B and C. Now let us understand what is qubits. In traditional classical computing, a single bit can be thought of as a piece of binary information denoted as either 0 or 1. That is, a classical bit can exist either in 0 position or in a 1 position, whereas the qubits can occupy the third state known as a superposition. A superposition represents 0, 1 and all the positions in between taken at once for a total of 3 separate positions or 3 separate states. While qubits can encode 3 separate positions, they are still used to convey information through a binary system. In such systems, the term bit can refer to either the material or the process used to represent a 0 or 1 or measurement of that 0 or 1. Now let us see the features of qubits. Come to the superposition. As I said earlier, classical bit can be either a 0 or 1, but a qubit can exist in a combination of both states at the same time. Superposition of two state means a quantum system is in two states at a time unless and until observed. And this superposition is very useful in quantum computing. For example, imagine a coin spinning in the air. It's not just heads or tails but both simultaneously. This ability to hold the multiple states allows quantum computers to perform many calculations at once. The quantum of superposition is further explained by the famous Austrian Irish physicist Erwin Schrödinger. He states that if you place a cat and something that could kill the cat in a box and sealed it, we cannot know if the cat was alive or dead until we open the box. So that when the box is opened, the cat may be dead or alive or in a superimposed state. And this is the illustration for the superposition. And next, coming to the entanglement, when two bits are entangled, there exists a special connection between them. It means that the state of one qubit is linked to the others no matter how far apart they are. This is called spooky action at a distance. Changing the state of one entangled bit will instantly affect its partner. This property enables powerful correlations and faster computations in quantum systems. Let us say that two particles are closely linked. One particle is at home and another one is at home. So whenever the behavior of one particle at my home changes, which will immediately affect the state of the other particle which is in your home or vice versa. Now coming to the quantum interference. Quantum computers use interference to manipulate the probabilities of qubit states. By amplifying the probabilities of correct solutions and cancelling out the incorrect ones, quantum computers can solve certain problems more efficiently. So these characteristics of quantum mechanics which makes the quantum computing very interesting to study and implement. See you in my next video on qubit representation. Have a happy learning. Bye bye.